Welcome, everybody. Thanks for coming. My name is Parashar Krishnamachari. My colleague Evan Brand and I will be taking you through our talk on the subject of cloud computing in the audio space. To begin with, I'm just going to give you a quick rundown of what we'll actually be covering in this talk. We'll start by talking about our motivations for going to the cloud. What is the reason why we think a software as a service model works for audio production and what's good about it. But of course, we also have to talk a bit about the challenges. There are obviously difficulties in trying to deliver such a service. And then the majority of the talk will actually be dedicated to our solution, what we actually do to address those challenges. And going from there, we'll be talking about further developments, things yet to be done, and things to be improved upon over time. And to close out, we'll talk mainly about our large-scale vision for the future of the audio space. And to kick things off, I'm going to hand it over to Evan to get us started.
I want to start off by talking about why move production to the cloud. Let's be clear, cloud for us doesn't just mean cloud storage or download on demand. The industry has this. We're talking about going a step further. What we mean is moving the actual processing to cloud compute and doing all the heavy lifting remotely. Going this route is better for the artist. It means being able to pay low-cost subscriptions and flexible licensing terms that offer artists choices they may not have had. Cloud compute is scalable, so as the demand for more powerful processing increases, that power will be available. This means it's device agnostic for the artist. You can manage the same projects on a monster rig as you can on a generic laptop. This is possible because the machine on the other end is the one doing all the work. Because that remote machine is a constant, it's possible to put different front-end UIs to that same back-end, so the UX can be tailored to the platform and style of workflow that works for each artist. It's not just the artists who benefit, it's better for the developers. When artists have more choices, the customer base increases across more tools. The precedent is that subscription models, even at modest rates, are more profitable in the long run. Just look at popular download-on-demand offerings. In an open cloud marketplace for tools like ones we are creating, more developers can reach more customers more easily with their full array of product options. By keeping everything sitting remotely, there is nothing that resides on the artist's device, so piracy will be reduced. It's a win-win for everybody. You have a venue that makes more room for more products to reach more customers, and that is a powerful means for accelerating the evolution of the industry. So if going to the cloud is so great, why doesn't everybody do it? One reason may be fear of change. The mentality is that what we have seems to be working. Why fix what ain't broke? And for those who do realize that the landscape isn't perfect, there's the worry of whether it would actually work out well. Another reason is a vested interest in the status quo. Some of the biggest players in the market already made their significant bets on the technology solutions long before the commercialized internet, much less 5G connections on our cell phones. Even a decade ago, this sort of a concept would have been unfeasible. There are technological hurdles to overcome when you go to the cloud. Among them, the elephant in the room is latency. Artists worry about latency when using a DAW on their machines. Over a network, you have latency and jitter. Usually the answer to that jitter problem is to use big, long buffers, making overall latency even worse. Given all that, is there hope? Yes. Let's just start with an example. This image is taken from a live stream by the YouTuber Adam Neely. Check out his channel if you're into music theory. The stream is from a collaborative production session done over a Zoom call. I'm sure you've experienced Zoom's latency. Yet, in spite of this, they were able to produce an album. Granted, this was during the height of the pandemic, so they didn't have many options. So it's encouraging. There are ways artists can produce and collaborate despite limitations of latency on a group Zoom call. But we can do better than that. Can we make latency zero? Not yet, but there is plenty of room for improvement. Broadband internet is going to improve, get faster, and more widespread. There has been significant progress in recent years, like Starlink. As Adam's session shows, not all workflow styles are equally sensitive to latency. When we talk about zero latency, that really means zero in the sense that there is no discernible impact due to it. Yes, live performance work like DJing would not be all that well served in a version 1 as compared to, say, mastering or compositional workflows, but that doesn't mean they never will be. Of course, having scalable computing power means that we can at least make the internal latency of the system effectively zero. But this highlights another important key point. There is plenty of headroom on the software side to improve performance and help bring the artist experience to the point where latency becomes inconsequential. To talk more about the way we actually go about it, I'm going to hand it back over to Parashar to talk about our solution.
Thanks, Evan. Let me just start before I tell you what we do. What didn't we do? What doesn't work for audio production? And really, the classical definition of a SaaS model doesn't work for audio production. What we usually think of as software as a service is a data-driven model, and it involves making a request, server finds the data needed, compiles the data in various ways, map reduced, and so on. The result is received and handled on the client as needed. This doesn't work for music production. Music is not a bunch of discrete chunks of sound picked from a pool. Things like context, flow, layering, timing, all of that matters. And for that, we need actual real-time interaction with the process. That's why we have DAWs. That's why we created these user interfaces that actually give you a view of how we put things together, the patterning, the layering, the harmonics, the data flow, the input and output. Uh, these are organizational tools that help us put all of our ideas together and try things out. And we need that continuity of workflow in real time. So the standard data-driven request and response model, one, it's too slow and it's too isolationist with respect to individual portions of data. So what does work and what did we do in the end? Or what works is a DAW, but it has to be split into two parts, pretty much like so. Now, I want to stress this is just a 10,000 foot view, simplified to a great deal. Now, the idea here is that the DAW UI is the only thing that sits on the client device. The actual audio processing, the plugin hosting, the playback, well, audio generation, I should say, is happening on a remote cloud VM. These two interact through a network layer. Well, this sounds simple, but simple and easy are not quite the same thing. If you think about it the same way we would think about it if this was just a single application locally sitting on your machine, which most DAWs are, of course, think about every single memory operation that happens when you make a change in your timeline somewhere. Or if you are trying to just play back or you're trying to do any sort of processing, there's a lot of there's a lot of things that happen. Eh, There's a lot of data that has to be shuttled around, and when it's happening on memory, it's quite simple, or at least it seems that way. But when you have to actually split that across two different devices, now you've got some problems, and that's where all the complexity and challenges come in. So that 10,000 foot overview is nice and all, but just saying that there's a DAW engine and plugins on the Cloud VM doesn't really say very much. So drilling down a little bit closer, it looks a little something like this. Again, still simplified, but That aforementioned DAW engine is the core functional component of this server-side host application. Now, you might see in this diagram that the connection to the client is direct from that host application, and that's actually accurate. It's one of the ways we reduce effective latency. We don't go through some extra layer or service like VNC, RDP, VMware, whatever the case may be. All of that functionality is integrated in the host app, and that means it's under our control. Everything is direct and on demand, as real-time applications should be. Now, that host application is actually hosting plugins, patch libraries, filters, loops, etc., that are coming from persistent storage and spun up into a local file system. Well, local to the host VM anyway. That what it actually gets is a subset of that is filtered based on the user database and so on. One important thing is that none of none of these plugins are really following any sort of new proprietary, yet another new plugin format. And that's one thing that separates us from a lot of existing web-based DAWs, which have to use a standalone proprietary format just because VST will not naturally work. But we are actually conforming to the de facto industry standards like VST and so on. As Evan alluded to earlier, we're trying to make an open platform for all developers to simply publish and make their products available on the cloud. Say you want to use Omnisphere or Silent or Contact, or say you're a VST developer or a creator of sample packs or loops. In principle, any one of those can simply be uploaded to this persistent storage as is without having to create a cloud-specific version of them. Now, in addition, the user does not have access to any of the content that they did not personally create. None of this is ever downloaded to the client device. The client merely has the ability to use that. And only the server-side host application really knows where any of them are, where they're stored, what state they're in, what data is being run through them. The client simply receives the processed results, never the original content. What access they do have is limited by the user credentials. What you see here, the plugin info database, plugin is in quotes here because I'm using it as kind of a blanket term to actually include things like loops and sample packs and patch libraries and filters and so on, not strictly just plugins. What it actually stores is information about where every individual product is stored, where where they will be spun up in local storage, what the licensing terms are, pricing information, and so on. The user database, for every user, there are references to entries in this database to say the user has actually purchased or subscribed to certain products, a specific subset of products. That means that only that subset is actually ever spun up to the local file system, and a configuration file is generated for the host app that just has been populated with a list of supported products. And that same list is actually published to the client, just the list, so that you actually see it in the UI. In essence, it creates a system in which the client side is a source of control, and the server side is actually the source of the generated output. So when we look at what happens on the client, it is principally a front end, which, what you see here is a development version, and it's a bit dated right now, but it was sufficient for actually testing things. What you actually see here is closer to our real target design for what the front end is going to look like. And principally, you don't necessarily see anything uh, new in the sense of we've invented some entirely different interface or so on. It should look familiar, and it's really there to provide a content creation workflow for you. this is the only thing that lives on the client end. So it should look familiar. It should also be usable, and that's what we're really going for. Now, in order to work with a remote host, though, this front end has to be able to encode changes, edits every time you say move a clip in the timeline or edit these curves or change levels, whatever the case may be. It needs to be able to codify that and actually send it over to the server side so that the two sides remain in sync. Now, because the client is mainly written in JavaScript, it's very easy to work with the JSON data structure. And on the server side, we use Juice, no surprise there, which works with value trees. They're very convenient when you're working with Juice. Um, and almost serendipitously, we actually arrived at a solution for this, which is very similar to the one presented in ADC 2019 during a workshop on the JSON value tree synchronizer. Um, they're not quite the same, though. The module in that presentation was unidirectional, and it so happened to favor the direction that was less important for our purposes. Ours is actually fully bidirectional, but the principle is really quite similar. In addition to being able to work with the server host app, it also has to interact with remote hosted plugin UIs. And the solution there is very VNC-like, but not exactly. More on that later. Um, and it also has to support peripheral device input. I mean, you need to be able to use your microphone if you want to record a clip. You need to be able to use your MIDI controller and so on. There are a number of web-based libraries for actually doing this. So um, in addition to that, there's all the secondary functions that it has to do that are unique to having a remote system, like sign in, user credentials, actually launching connections, keeping a local cache of the working project file, and so on. But on top of all that, we're forgetting something rather important. It also has to play back audio. Shocker, I know. I'll give you a moment to collect yourself after that bombshell. And just to give you a little feel, let's take a look and listen. Okay, so I did say before that the screenshot that you saw on the slide earlier was a bit dated. And here is a view of a more up-to-date build. Um, as you can see, it's much closer to that target design, but still very much a work in progress. Now, the test case that you're seeing here just has a simple audio clip in a track, and we'll give that a go. Okay, now the next step is to instantiate a plugin and wire it in the graph. Yep. So this is just a simple test case, not particularly exciting per se, um, but the idea here is to simply validate that a few core functionalities work. One, that we can actually play audio clips. Two, that we can actually host a filter plugin. Three, that we can actually edit the graph, and those connections actually um, alter the audio processor graph that is actually used in the engine itself. So those changes are reflected, and the processing of that plugin from the original clip data actually works. So this is being tested on premises,
So not using a cloud VM per se, but again, when we're trying to test core functionality, we care more about that core functionality rather than the supporting infrastructure around it.
All right. So how do we actually get that audio in the first place? So updating from the client, it happens very frequently. So it has to be made up of very compact messages. And in order to be able to do that, we need to be able to locate very specific portions of data in the project file as tightly as possible so that the smallest possible message can represent any particular edit, any particular action. And that translates more or less to a very strict hierarchy. Well, that's convenient because value trees are exactly that. Having very localized data also opens up possibilities like referencing and instancing because you can actually refer to each element by a path. And that allows you to do things like copy paste as an instance so that a change that happens in one location is propagated to all locations where that instance occurs. So the overall structure looks a little something like this. Now, this is not real data per se, but it's representative. We have a collection of processors. We have a processor that may have other processors underneath it. Now, those could be plugins, it could be filters, whatever. And we have connections between processors for data flow. Outputs of one is going to the input of another, and so on, as well as any data pertinent to that specific processor, and so on. And this is all in a larger collection. Now, outside of this, there may be other data, but this is just an example of one specific thing. So the simplest way we can think about it is that everything is either a processor, an audio processor of some kind, or it's data that is pertinent to that processor, whether that be settings or input data that processor actually uses. The, the input-output chain, as you see through these connections between processors, is effectively uh, the equivalent of an audio processor graph. And that's actually what we use within Juice. Now, tracks themselves that actually contain all of this can be treated like synths that exist in that graph. And they're essentially synths that output whatever is coming along their respective timelines. And when you actually layer all this together, you have your tracks, you have the processors within them, you have their respective graphs, you have you have all of that being output to the mixer table and to the master output. When you reduce all of that together, well, you can reduce the entire project file to a single directed acyclic graph. So this is this is the core of our audio engine in essence. You reduce all of it to one graph and it becomes a single processor that we actually run everything through. So now that we're actually generating audio, how do we get that audio over to the client? Well, you can think of it as a one-to-one audio live streaming engine. The flow is pretty simple here. The audio buffer is generated per frame. That audio buffer is encoded for transmission, and that buffer is streamed to the client. Now, when you think of live streaming, normally that actually is a process that has a lot of latency because there's a server in the middle that actually does all the preparation. But those are for live streaming applications that are broadcast to many, many viewers all at once. So you do need that man in the middle for that reason. In our case, it's really happening between one server and one client most of the time. Now, in collaborative sessions, there may be multiple There may be multiple users who are connected to the same host application instance, but even then, it's very likely that only one will actually want to be listening at a given moment. So really, the streaming happens on a one-to-one basis. Now, one of the things about this process is that we essentially wrapped this up inside one audio device. Now, the reason we did this is because when we're actually working as developers, we're not necessarily going to be testing a live connection to a client all the time. We might actually just want to be developing on that host application. And when we're doing that, we just want to play back onto our local audio device. And that'll be the setting that we put in place so that we can actually listen, make sure that that audio engine is working properly. But when it's actually in use, the default audio device will be the streaming audio device. Uh, this is one of the other ways we actually make sure that latency is reduced because there is nothing in between the encoding and the buffer being streamed. It's all happening right away. So the same frame time where there's an audio buffer being generated is when it's being encoded, and that is when a message is generated to be streamed to the client. So streaming, we have a couple of actual ways, to deal with this. I mean, this is the real source of potential latency. It does happen to be that reducing bandwidth with a compressed stream helps us with latency by helping reducing the delay of the transmission itself. But the codec that you use can also be a source of latency. Now, the simplest type of codec we could use is just raw PCM data. Now, the nice thing about it is it's the best possible quality, it's very simple, and there's no additional latency to it. But of course, it's higher bandwidth. You know, 44 kilohertz or 48 kilohertz 16-bit is at least 1.5 megabits per second transmission. And if you have uh, even more channels, for instance, it gets worse. Another option is MPEG or MPEG-like audio compression. Now, the nice thing about it is it's quite low bandwidth, and it is actually very good for the bandwidth you get. And obviously, you could go into very low bit rates where the quality suffers a lot more, but for live listening, as opposed to, say, the raw output, um, it can actually be quite good. Uh, However, it also introduces an inherent latency, and much of that actually comes from the entropy coder, which in general needs a certain number of actual symbols to be generated before it can actually result in any sort of decent compression ratios. So that actually usually happens in MPEG encoders by either padding the the initial frame or by simply having no output for the first frame and only on the second frame. It actually outputs some real data, which is actually the frame behind. This is this is arguably not as huge a problem when you're actually streaming, but it actually becomes a bigger problem when streams are stopped and started. And on top of that, MPEG audio itself has limited stream layouts, but you can, in order to support things like, say, 5.1, you will probably have to include things like AC3 or OGG Opus and so on. But something else on the horizon is our own in-house codec, something that is still very much experimental, but might as well talk about it here. It is a low complexity codec, and it works entirely within the local buffer and outputs a progressive stream. Now, you might say that conventional wisdom says that this shouldn't be very good for compression ratios. Conventional wisdom is correct. It isn't that great from from a compression ratio, it doesn't quite equal that of MPEG audio or Opus or anything like it. But that isn't the focus of this codec design. It's really about the zero latency effect. So it's a moderate bandwidth demand, certainly better than raw PCM, and it does not have any stream layout limits. We can always add more because it's our own, but it's zero additional latency. Latency is the number one focus for it. Now, putting all of this together, we can get a good general overview of how things have to move in order to get things going. So, step one, the user signs in. Now, step two, a query is made to the load balancer to find and spin up a VM. Now, really currently this means a whole VM, but in practice, multi-tenancy will be necessary in order to keep costs down. Now, the query returns back the external IP and the selected port on the host VM, but the host application has to be started with that port as well. Then the user's record is checked in the database in order to find things like their personal storage, what other products they've actually purchased licenses to, and then that list of products is reported to both the client and the host application. So the host application gets a configuration file that says only these products are available as far as what they can access. And similarly, the client side will get that as a list that just says these are all the tools you have, besides any clips that you have stored on your own local device. And then a project file is loaded on both sides. Now, most of the time it'll just be the initial empty one, but if you actually want to start up while loading a specific project file, the project file is loaded on both sides and editing can begin. These are all the steps that take some time at the initial sign-in, but don't take up any time afterwards. So what does the actual network traffic look like when we're running? So first of all, we have our client-side UI and our server-side host applications. The majority of things that you do on the UI are going to generate file updates and edits, those little JSON patch messages. This is probably the most critical part because the two sides need to remain in sync with each other. In addition, we also send commands and actions. So this means things like play, stop, load or save a file, move to a particular position in the timeline. All of those are actions so that state is actually up to date on both sides. Now, nearly all of those file updates and edits happen on the client side and are sent from the client to the server, but some updates also happen on the server side and have to be sent back to the client. That is because plugins, patches, samples from third parties are only stored on that remote side, so only the server side knows about it. When you're interacting with those plugin UIs, those changes happen on the server side. So again, those settings updates have to be reported back to the client again so they stay in sync with each other. So of course, streamed audio, anytime you hit play and you're actually listening through it, you're listening to the streamed audio output. But there's also streamed video. Why? Again, going back to those plugin UIs, we do a sort of VNC-like type of thing for each plugin window, and that actually is a video stream. There's also related to that peripheral input like keyboard and mouse and so on. Now we don't go through a separate service. It's all integrated inside that server-side host application, and processing the results is also completely integrated into the client-side UI. Again, this is one of the ways we actually keep that latency down. One of the other things about it is that if you're not interacting with the plugin UI, this bandwidth is not used. So we manage bandwidth tightly that way. We can turn it on and off as needed. So having said all that, what still remains to be done? And I'm sure you've actually surmised this based on what you've seen so far, but in full honesty, things are still in a prototype phase. And it serves to prove out the concept and everything, but so far we're still developing things that are on the critical path more so than anything else. So it still remains to flesh this out into a proper usable tool, going into beta and going into a version 1.0. For the same reason, we want to expand the included tool suite, built-in filters, built-in synths, sample packs, as well as an existing library of third-party tools and so on that can actually be made available for purchase. Going beyond that version 1.0, of course, we still want to build out those multiple front ends. And one of the really powerful things about splitting the DAW is that you can have different workflow look and feel designs. You can have workflows that are very focused on things like mixing and mastering. You can have something that is very MIDI composition focused, something that is very recording or clip focused. You could even do something meant for beginners, like a garage band versus Logic kind of thing. And the nice thing is the power that is available to them is the same because the back end is consistent. Now, we've talked a lot about security because we keep the plugins and the uh, tools and so on stored exclusively remotely and never made available to the end client. That helps with piracy, but we also want to protect the rights of the artists. And a trivial thing we can already do right now is just encrypted project files so that, and it uses a key unique to every user. But the next step from there is to move into an NFT market. Now, the real purpose here is that a blockchain can actually store not just transactions, but also contracts and agreements and so on that gives the user a lot more control over rights management. And this is also part of our commitment to making sure that there are no loose ends in that. And beyond that, we still want to make continual improvements to the underlying technologies. Still want to add more features, support new technologies as uh, technology advances, keep improving performance, keep improving latency. And beyond the things that we want to do, though, there's also the larger vision of how this relates to where we see the industry going in a post-SaaS world. And to talk more about that vision, I'm going to hand it back to Evan.
We may be less than 3 to 5 years out from ubiquitous bipedal robots walking and working among us from the likes of Tesla, Amazon, DARPA, and others. How about ubiquitous artists creating among us? Our offerings are minimal latency, minimal cost, and have minimal hardware requirements. Our vision is to enable 1 billion current and future artists to get in the creative flow without costly impediments. Billions of more creators accessing our solution with potent AI will accelerate breakthroughs in both production and audience experience. I'm aiming for a future where the number of empowered creators far exceeds the number of terminally uninspired, unproductive, and uncreative, pernicious social media trollers. With any luck, this technology and culture template will empower other industries to accelerate the recursive improvement too. Would our culture's evolution have it any other way? Would you? Our solution supports a grand vision of democratizing art and elevating our culture's creative heart. If you feel my flow, join us for the ride. The choices we make today materially impact who we are as individual creators and a culture. Thank you for joining us.
All right, thank you very much. So I guess we'll hand it over to questions, if there are any questions in the room. Tom, do you want to come up to the back to the laptop, ask your question. Yeah, we got one here from Tom.
It's the other elephant in the room, actually. It's how do you scale your VMs reliably and in a way that's not going to spiral out of control in terms of costs and, network load, that kind of stuff?
Yeah, a big part of that actually relies on collecting data from users of various tiers. Part of it is that there would actually be some tiered allocation of virtual machine power based on, is this user more of a hobbyist, or is he like doing much more serious large scale production or something? And that in turn also affects their service pricing and so on. But when you actually collect that data, you can actually find out what is actually optimal in terms of how big of a machine do you need to use and how much multi-tenancy do you need to support. I don't know if that completely answers your question, but
yeah, it does. Yeah, thanks. But generally speaking, what you're saying is you've got your audio rendering engine is running inside its own virtual PC. So it sees it's almost running like a typical operating system environment.
Yes.
Right? Okay. Yeah. Okay. Understand. Okay. Thanks.
Any other questions? Doesn't look like we've got any. Oh, there's one popped up in the Q&A online.
Mm-hmm.
So we've got a question from Andros, who says, wouldn't professionals prefer to keep using their fave door UX UI, or is there a plan to have a standard and make it possible to integrate existing doors as clients or front ends to your streaming / backend service as an alternative to using an entirely new door client?
So I suppose it isn't 100% impossible to have a UI from another developer actually be a front end. The main thing is that we actually control the data format at play here. So, and we kind of have to do that in order to be able to map very well between the messages that are sent for keeping the server side in sync. So if another developer wants to be able to load and save files that are actually in the format that we use, that is theoretically doable, or if they have some way to translate between that data and their own format. But the easiest thing to do really is for us to build a DAW UI UX that is very similar to that product to make it as familiar as possible.
Great. And I had a sort of similar related question, which is, you mentioned plugins running on the server side. So how do you envision users who have maybe already a suite of plugins locally that they won't then want to use in their production in the DAW?
Yeah, that boils down to a lot of the problems there are more legal than technical. If it's a question of being able to host those products on the remote server side and be able to convert a just already purchased license saying, okay, you already own a license to this product, so you don't have to make an extra purchase on our end.
Yeah. So you'd envision having the plugins already existing on the server side, and then the users just authenticating, and it's serving that to them. Okay.
Yes.
And there's another question online from Ryan, which seems similar. So are there plans to allow the front end usable without the back end and its plugins? I think many pros would be concerned about having to cancel sessions if their internet connection goes down.
Yeah, I can definitely see that being an issue. One of the things that the client side does have to do is keep a local cache of a file on your device, so that if the connection fails, you can actually restore from that backup that you have locally. And that also means that any edits that happen after the connection fails will still be around. there are things you could do in theory, but I'm pretty sure it would be pretty limited, at least in terms of being able to get a processed playback on the client side without if your connection fails. Certainly, if you are just dealing with clips or something or an already existing rendering, you might still be fine.
All right. Do we have any more questions in the room? Yes. Yeah. Do you want to come up to the mic?
How does the recording work? Are you record locally and after that you upload it to the server, or how does it work?
Yeah, that's basically it. You will have to buffer the recording locally and send that upstream. It's much more reliable to do it that way, we found, as compared to, say, streaming packets that one little bit at a time. That may change if broadband connections that are really fast, like, say, 5G, actually become more ubiquitous. But for the time being, that's pretty much how it is.
Thanks.
Any more questions? Okay, in which case, yeah, thank you very much for the talk, Parashar and Evan, and yeah, thank you very much. Round of applause.